Hello, today we want to deal with the differential quotient. It is about the fact that you can determine the slope at a certain point for a function f of x. That is the gray line of a very general nature. You know that you could determine the slope in middle school, for example, for a straight line equation where m was constant by f of x2 minus f of x1 by x2 minus x1. That was constant over the entire straight line. Here it is different. The slope changes at every point to f of x. I have now drawn in a selected point here with x0 and f of x0, and we want to calculate the slope at the point x0, f of x0. To do this, we add a second point, which is identified by the coordinates x0 plus h and f of x0 plus h, and form a slope triangle. That is the triangle marked in red in the figure. The slope can then be written as follows: f of x0 plus h minus f of x0, which expresses the y difference, divided by x0 plus h minus x0, i.e. by h. The special thing is that the slope changes at every point on the curve, that you now allow h to become smaller and smaller. That is, the second point f of x0 plus h gets closer and closer to f of x0, and the slope triangle gets smaller and smaller and constantly changes during the change, namely in the same way as the curve. The whole thing is expressed by limit h towards 0. In the differential quotient here, you can see a real function, the blue line, and how the red point moves to the blue point, and the gradient in the blue point is calculated more precisely the closer the red point approaches the blue point. You can see very clearly that the green line hardly changes. I would like to illustrate this using a few numbers for those who have difficulty dealing with variables. In the example, x0 is 5 and x0 plus h is 5.5. F of x0 plus h is 3.5 and f of x0 is 3.2. Then f would be the line at point 5. So for x0 equal to 5, 3.5 minus 3.2 divided by 5.5 minus 5, or h, would simply be 0.5 in the example. The difference 3.5 minus 3.2 would be 0.3. That would be a first approximation, still a very inaccurate one for the point x0 f of x0, but a first approximation. The numerical values are fictitious and do not play any role. It is only intended to be an illustration of how the differential quotient calculates the slope at a point. I do not want to go into the second part, with the second numerical values. It only shows that the slope triangle is getting smaller and a different y numerical value and a different h value exists. For the general example 1, f of m times x plus b, we want to calculate the differential quotient in general. So we have to insert x0 plus h into the straight line equation for x, and then it follows m times brackets on x0 plus h brackets closed plus b minus f of x0 is at the top in the differential quotient, so minus brackets on m times x0 plus b. We have to divide the whole thing by h, and finally let limit h run towards 0. Let's look at the thermal model. Times x0 multiplied from the first bracket, minus m times x0 cancels out b. Minus b also cancels out, also becomes 0. What remains is m times h divided by h, and m times h divided by h is even. H cancels out. What remains is m. H towards 0 plays no role in this case. So we have m, and thus the expected result that the slope for a straight line equation is constant. It is important that a constant obviously becomes 0 when differentiated. This can also be easily illustrated by if f of x0 plus h is constant, 5 for example, and f of x0 is also 5, then 5 minus 5 divided by 0 and 0 divided by h for h towards 0 gives 0. You will see the second example of how a function for f dash of x comes out in the next video. See you then. Thanks for your attention. Bye.